Okay, this is chapter 19, problem 19, and in this problem we're shown a figure 1950, which I've tried to reproduce here, in which there are 1, 2, 3, 4, 5, 6 resistors hooked up in this way with a battery, and we are tasked with figuring out what the net resistance is, or what is the equivalent resistance. So what I'm going to do is I'm going to take us through a series of simplified diagrams where we find the equivalent resistance of smaller pieces, and eventually we'll be able to figure out what the equivalent resistance for the whole circuit is. So first of all, we should highlight this piece here. If you notice, what sticks out to me is these two resistors are in series. And so if you like, the equivalent resistance there should be the sum of this one plus this one, because let's keep in mind, when we have series resistances, the equivalent resistance is found by simply adding up what's there. And recall that in parallel, the equivalent resistance is found by finding the inverse of the equivalent resistance. That is determined by adding up the inverses of all the resistors. But at least for this one, it's nice and simple. The equivalent resistance for 1 plus 1 is simply them added up. So if you like, the equivalent resistance here should simply be 2R using this formula here. So a simplified diagram then looks something like this. I'll kind of draw it like this. This is the 2R, and the fact that this wire is curved, that really makes no difference, and I can make it longer or shorter. The actual piece of the conducting wire is thought to be, is treated as perfect resistor with no resistance in it whatsoever. So this should be the remaining, if you like, equivalent diagram that would give us everything that we need. There's the battery, and that should do it. Okay, and now that I look at this, what I notice is that, well, these two, this one and this one, these are in parallel. If you think about it, as I take my finger from the edge of one resistor, I can go through all this conducting wire, no change in potential. To here, that means these are at the same potential. Likewise, I can do that over here. These are at the same potential. So these two are in parallel, and so I'm going to need to use this formula to figure out what the equivalence resistance is for these two. So for this, I'm going to follow the formula. 1 over equivalent resistance is 1 over one of them, in other words, 1 over 2R. Add to that 1 over R, a 1/2 plus a 1, that gives me a 3/2 times 1 over R. And to find the equivalent resistance, I take the inverse of that. The inverse of 3/2 over R is R times 2/3. If you like, this here is 2/3 times R. So the equivalent diagram for this should be something like this. I'll draw the original pieces. There's the battery. And then something that kind of does this. This here is 2/3 R, while these are still R. Okay. Now as I look at this, it seems to me that this one and this one are in series together. Well, series is nice because I can just simply add those. 1 plus 2/3 is 3 over 3 plus 2 over 3 is 5 over 3. So this is an equivalent resistance of 5/3 times R. Okay. So the simplified version of this is something that kind of looks like a 5/3 R. And again, the fact that I've made this at a right angle is meaningless. I'm just drawing it this way to make it look simpler for my own purposes. This is R, and then this is R. There's the battery. Okay, we're almost there. Now that I've drawn it this way, in a perhaps suggestive kind of way, these appear to be in parallel. Just checking to make sure I haven't screwed this up yet. These are in parallel. Okay, let's figure out what their equivalent resistance is. 1 over their equivalent resistance is equal to 1 over the resistance of one of them. In other words, 1 over 5/3 plus 1 with R in the bottom. Okay, 1 over 5/3. Well, remember, when you divide by a fraction, that's the same thing as flipping the fraction, bringing it up top. That's 3/5 times 1 over R plus 1 over R. 3/5 plus 5/5 is 8/5. If I didn't screw that up too badly, 8/5 times 1 over R. And don't forget, you have to take the inverse. And so what that means is the equivalent resistance here is apparently 5/8 times R. And now we're pretty damn close. Because the final thing, and you can perhaps see this, is that you've got this equivalent resistor of 5/8. The equivalent resistance is 5/8, and this one remaining are, these two are in series together. Okay, so finally, adding these all together and getting our equivalent resistance 5/8 plus 1 8/8, in other words 13/8, 13 over 8 times R, and that final, if you like to have that final diagram, it would look something like this. The battery, something that looks like this, has a resistance of 13/8 times R, and that would be enough to figure out what the equivalent resistance is. It's apparently 13/8 times R, and that would be enough to figure out what the current is flowing through the entire circuit. Check my math. It is in fact 13/8 R for your final answer.